Good, and now it's again time for examples. And when I say examples here, I mean examples for how to choose these projections. Okay, and thereby, of course, examples of how to construct projection methods when you're given an operator A. And for the sake of completeness, let's start our list of examples with our truncation operators that we met before in LP when we introduced the finite section method. So this n down here tells you how many of your entries will survive, and then the rest is all being put to 0. Of course, you can do the same construction for two-sided infinite vectors, and we also saw that happening, in which case you would typically truncate from -n to n. Okay, I'm only giving examples here for the projections Pn, and that's why I'm only writing down a space x and not y. But of course, everything I'm doing here with Pn can also be done with Pn hat instead. Great, next example. So LPR, let's look at functions on the real axis for which the modulus to the power of p is integrable over the whole axis. And such functions will always have to decay to go to 0 as x goes to plus or minus infinity. So they usually look a bit like this. And what you could do is you say, okay, I just fix the interval -n to n, and all the data between -n and n will survive, and the rest outside is replaced by 0. So if this is your function f here, then your function Pnf will have a graph like this. It is the blue function between -n and n, and it's 0 outside. You could simply say that the operation that's happening here is multiplication by the function that is 1 between -n and n and 0 outside. And if you think about it that way, then it's clear that this is a projection. If you do it again, you get the same, like after the first application of this operator. Okay, and it's also easy to see that if p is less than infinity, then these projections will converge strongly to the identity. And the same, of course, here in our first example. We did this computation before. We should just remark that p be less than infinity here. Okay, so the properties that we have to check in all our examples are whether Pn is a projector and whether it converges strongly to the identity. Okay, so in the first case, the image of Pn, which is going to be our space capital Xn, is n-dimensional and hence finite dimensional. So you can immediately work with n by n matrices there. In the second example, the image of Pn is still infinite dimensional because, well, in this interval from -n to n, there's a lot of data to be stored, and we discussed this even for continuous functions, that the dimension of a finite or of a bounded interval is infinite. So even more so when you give the functions more freedom here. If you like this idea of identifying a projection or a truncation Pn by the operator of multiplication by a function that is 1 somewhere and 0 elsewhere, then of course you could also interpret this truncation here as component-wise multiplication of the input vector by the vector that is 1 in the first n entries and 0 in the rest. Okay, next example. Let x be the space of all 2p periodic functions on the real axis. Values could even be complex or real, as you like, for which you can integrate the square of the modulus as long as you only integrate over an interval of length 2p. So you could, for example, integrate from 0 to 2p, or you could integrate from p to 3 times p. You're going to see the same values anyway, so it doesn't matter where you look. So we could abbreviate like this. We take functions f, which if you restrict them to the interval from 0 to 2p, so you're only looking at this bit, then you get a function in L2, so the squares of the modulus are integrable, get you a finite integral on the interval 0 to 2p. Okay, so if we call them f here, then we should probably call them f up here also. And like I said, it doesn't really matter where you start integration and end integration here, as long as the interval has length 2p. You're going to see the same values anyway. You've probably seen this space before, and I think you agree that this is quite clumsy to write it down like this and to explain it like this. So we should try to find a somewhat shorter way to denote the same space. I mean, we could of course say that we're only interested in functions on the interval from 0 to 2p. And then express this wish here by saying that your function be in L2 from 0 to 2p. But then you still have to say that somehow you're looking for periodicity. So you're expecting that whatever the function is doing at the right endpoint of your interval, it should also be doing at the left endpoint of your interval. You could of course avoid that by making your interval only containing one of the two endpoints and not the other. Or you could try other things, but if you ask me, then the most elegant thing to do is to take this periodicity condition and stick it into the geometry of your interval 0 to 2 pi. So what you're saying is that you want to identify this endpoint with that endpoint. Then it's of course natural then that whatever the function is doing at one endpoint, it's also got to do at the other endpoint. And what I mean is that instead of talking of this interval with two identical endpoints, you're talking about a circle. Okay, and if we then take this to be the unit circle in the complex plane, then we could just say that the number we are writing here corresponds to the angle that your vector or your point on the circle has with the real axis. And if you call that angle t, like we did up here, your point will just be e to the I t. I'm sure you remember that. But of course you can also write it as cosine t plus I times sine of t. Okay, so long story made short, instead of saying that we want an L2 function on the interval with a certain periodicity condition, we will just say that we want f to be an element of L2 of t, where t is the set of all complex numbers z with absolute value equal to 1. So it's the complex unit circle. Okay, so that's what I mean by putting this periodicity condition, which was usually originally a condition on the function f, into the geometry. So we make the domain periodic, and thereby we can forget about this condition. Okay, and now the 2 here in L2 suggests that we might have a scalar product, and let's try it with this. And you can show by the same arguments as we did before that this is indeed a scalar product. And then you look at the following family of functions, which is enumerated over the integers, not just the natural numbers, where bk of z, for z point on the unit circle, is essentially the monomial set to the power k, slightly scaled by 1 over root of 2p, and we will see why we want the scaling. If you're not too happy yet with working with these complex numbers set, then of course you can also rewrite this by writing e to the power it instead of z, where now t is a real number between 0 and 2p. Then it turns out that this family here is an orthonormal basis of our space L2 of the unit circle. So you simply have to check that any two of these functions are orthogonal to each other in the sense that the scalar product is 0, but that's easy to check. Then each one has norm 1, so you're putting bk in the scalar product with itself, and then because you do the scaling exactly right, you get 1, which means they are orthogonal and normal. Okay, and the fact that they are a basis, which is Schauder basis, is a bit more difficult to show, but yeah. One has to show that every element of L2 can be approximated by finite sums of functions like these, and this is what you do in Fourier analysis. I mean, what we're developing here is exactly the Fourier theory. Okay, so here it's written down again. Every function from our space X can be written as the limit, so this is a series here, so it's the limit of a sequence of finite sums of our basis functions pk, and these scalar coefficients alpha k here are exactly what you call the Fourier coefficients, and this expansion here is what you call Fourier expansion of f, or Fourier series if you want. So here we write a function as a linear combination of functions, or in fact a limit of such. Well, maybe you're more comfortable if we spell this out, what it means for function values. So if you just plug in the definition of our functions pk, then you either get this line here where your variable set is from the unit circle, or you get this expression with t from the interval 0 to 2p. Because this family pk is an orthonormal basis, we know exactly, since first year linear algebra, how to compute these coefficients here. Just get them as orthogonal projections. So here's the formula. You just project your f into the direction of your kth basis vector. And because it's even orthonormal, this denominator here is 1. So we can simplify, of course. And if you spell that scalar product out and plug in here what we know about pk, then we just have to simplify this complex conjugate here. We arrive at this formula here for our alpha k's, and this formula you've probably seen before, maybe with this or different scaling, but in either case you will call it a Fourier coefficient. And then one can look at the so-called Fourier transform, usually denoted by a curly f. And this transform takes a function f from our space X and maps it to this whole sequence of Fourier coefficients that you need to combine your function f from your Fourier basis, this orthogonal basis, orthonormal basis here. And again, because pk is an orthonormal basis, this Fourier transform here turns out to be a unitary map. or in real spaces you would say orthogonal map. So in particular, it's not changing lengths, it's not changing angles. So you can talk about scalar products also on the other side, and they will not change under this map. So you get that your sequence of Fourier coefficients is an element of the little L2 sequence space, and that the scalar product of two functions here is invariant under this Fourier transform. So these here are now sequences of Fourier coefficients, and just to avoid confusion, I'm writing little subscripts down here for the spaces where the scalar products are coming from. So in the same style, or even as a consequence of this here, when you put f equal to g, you get that the same holds for norms, where this last one here is usually referred to as Parseval's identity, and the previous is Plancherel's identity. But now, after this little intro into Fourier analysis, we are ready for the introduction of our projections. And Pn takes an element from our space X, so function f. And we know that we can write this in terms of its Fourier series. And the most natural idea now is to truncate the summation, which is going from minus infinity to plus infinity. Let me write it like that. And to truncate it to the partial sum that only goes from k equals minus n to n. So you're performing the same truncations as we did in our sequence spaces, but now here on the level of Fourier coefficients. So you're not truncating this function, you're truncating its infinite sequence of Fourier coefficients, or as engineers say, you reduce consideration to finitely many Fourier modes. And indeed, that's what engineers are doing all the time. They're just not talking about it. They just do it. Good. Well, that was a quite long example, but I think a very important one. Engineers use that all the time